It's always a pleasure to be here at QCon. I always learn so much. I hope to teach you a little bit, or to tell you a little bit about my story, sort of around events, appreciating events, and I mean how I see them being useful in implementing modern systems today. So I try to. It's a little bit theoretical talk. I'll try to sort of teach you sort of how to think in events and design around events, and hopefully you can sort of apply that in practice when you get home eventually. So, but why should you care about events at all? I mean, why do I think that they are important? In my experience, events can help us with a ton of things. They can help us drive autonomy, reduce risk, help us move faster with reduced risk. So help us to increase things like loose coupling, write more stable systems, write systems that can really sort of take on more and more load, scale elastically. I mean, to really take advantage of the sort of promise of cloud computing and sort of pay as you go. Increase resilience of the system, help you sort of to recover from failure, increase traceability to understand, like observability into the system. And also sort of funky things like time travel that can be really helpful also to sort of understand what went wrong, understand systems, etc., debuggability and things like that. The question though is like, why now? I mean, there's a lot of talking about events. Event-driven architecture is really hyped again now. The question is why? I mean, events have been around for decades. I mean, I've been using them myself for about almost 20 years in different settings and situations, etc. So why the sudden hype around events? I think it's essentially four things. It might be more, but I've sort of distilled four sort of key drivers, I think, to events. The first one is the move to cloud and multi-core architectures. Events really help us to take full advantage of that. It fits very well with that type of architecture. The second one is a move to microservices and distributed systems in general. And another one is sort of this move to more data-centric applications, like apps that are sort of more driven by data, that need to react to data in often close to real time, and how we can sort of do that while dealing with all this sort of massive data that users produce today, all with low latency and high throughput. And also that there are customers, they just want more and faster. They want more features, more data faster, they want better uptimes, they want better response times, etc., etc. And they have learned to be very, very picky as well. So, but let's start with the basics. What is an event? Okay. Event is sort of an immutable fact of information. Okay. Knowledge can only grow. You can only add knowledge. You can't sort of retract knowledge. So since facts are really sort of events or facts, and facts is all about knowledge. So that means that facts can only accrue. You can only add facts. Okay. This means that sort of events and facts, they can be disregarded. I mean, if you receive a new piece of information, you can choose to not believe in that. It might conflict with your existing facts or understanding of the world, right? So you can disregard events, facts. But once you have accepted them, they can't be retracted. Really, they can't be deleted. There might be new facts that arrive into the system, right? That sort of question the facts that you already have. But you can't go back and delete things that you already have accepted. So knowledge can, of course, change, but it's only changing by accruing more and more information. Okay. So events and facts can actually invalidate existing facts. We do that all the time. So this is my view of facts and how they relate to events. So events is sort of the materialization of a fact. Sorry. Oh, this one stopped working. Okay, so what about event-driven services then? How can you define an event-driven service? Well, the first thing it does is that it receives and reacts to facts. Facts sort of arrive. You might subscribe on facts, right? And sort of facts arrive into that service. So that might sort of react, cause some sort of reaction. And out of that reaction, you can create new facts that you then publish to the rest of the world, sort of based upon what you have understood, what you have sort of reacted on top of that. And event-driven service, in a way, sort of helps us invert the control flow, right? And this can really helps us sort of minimize coupling between services. That's sort of that you are so events just sort of arrive as they sort of happen, and you react to them as they arrive, without sort of being dependent on that a certain action should happen in a certain object or service at a certain point in time. Okay. So there's a lot of talking here about the events. They are immutable. The question is then mutable state. I mean, does that have a place? Of course it does, right? But I really believe that mutable state, it needs to be fully contained then within that service. So once you receive like immutable facts arriving to your service, sort of things that you sort of can accept as being the truth, then you sort of perform some sort of service, some sort of action, some sort of side effect, right? And there you can use sort of mutable state. But it's extremely important that mutable state then is sort of non-observable to the rest of the world. That others sort of can't see that. Instead, it should only be used for local computations, ideally at least. So, and sort of once you're done with the processing, once you sort of reach some sort of consensus, right, internally with sort of and done your processing, etc., then you're ready sort of to tell the world about your results, whatever that might be. Then you create an immutable value, sort of representing that understanding, or that thing that you want to sort of tell the world about, and you publish that as an immutable value out to the rest of the world. Okay, so mutable state is something that you only use internally, ideally, and you receive immutable facts and you publish immutable facts. That means that others now can sort of base their reasoning on stable values, things that they know, other services know won't change, that you can't just retract. So if we'll take a little illustration, let's say we have some sort of user here. And this user sends a command to some sort of service. It ends up in this mailbox or queue. And that sort of service then picks it up and does some sort of processing. Now this service then, as a result of this processing, then can create an event representing the outcome of that. What you want to tell the world that they should be interested in what happened. And that's sort of published in an event bus or an event stream. Okay? That event stream then can then relay these events to other services that are subscribing to the kind of event that you have just produced. Okay? It ends up in their mailboxes, and some processing happen, etc. Right? That also might generate new events, etc. So this is a way you can sort of hook up communication between services. But it doesn't have to be that it's only other services or components that sort of subscribe to your events. It might be that your events are pushed down into some sort of database, SQL database, NoSQL database, or for HDFS, for example, have like Spark jobs pick it up later for doing like big data analysis or streaming using Flink or something like that, or that you want to sort of hook up sort of other systems or other subsystems, to your system. So the listener of these events can be almost anything, which is really interesting. And one key aspect here is that this whole world is sort of eventually consistent. All of these events flow in a fully asynchronous fashion. This means that there aren't any transactions. Like there's not strong consistency. I really believe a strong consistency is really is overused in our industry in general. It's the wrong default. Sometimes you absolutely need strong consistency. I'm not saying that. But it should not be what you reach for as the first thing. It should be sort of a rare thing that you model when you absolutely have no other options. I think going all in on eventual consistency gives you a lot more headroom for things like scalability, resilience, loose coupling, having multiple teams, develop software independently of each other and just roll it out, and then having, the protocols between these services define the relationships. Okay. So in this way of using the event stream means that you can use it as a communication fabric between all your services. You can use it as an integration fabric, sort of integrating other sort of systems, other types of infrastructure, etc. You can use it as a replication fabric, to replicate changes for resilience and these type of things between data centers, between cross nodes, etc., whatever is needed. And you can use it as your means of consensus to reach agreement between services, using a lot of different techniques. I mean, CRDTs that Martin Kleppmann talked about yesterday is an excellent way to try to reach consensus, in a fully sort of decentralized and eventually consistent fashion. But there are other techniques as well. And you can use the event stream as sort of the foundation for persistence, as we will talk about later. So a lot of things open up when you think about the world and think about sort of truth and facts as events being sort of emitted in an asynchronous fashion over a reliable medium. But it's very important that we have to rely on eventual consistency. Again, but I think a lot of people get sort of worried about that. But I think, the best way is to usually just take a step back and think, how is the world actually working? The world is eventually consistent. There's really no such thing as strong consistency anywhere in the world, really. So if we just take a step back and try to think, how should we model this in the real world? How do we model it with humans or companies or cars or whatever? And then just try to map that to software. Usually makes a lot of things fall into place. We usually just reach for strong consistency and the whole is SQL database just out of habit because we think it makes things easier, and it does, until we want to achieve the traits like resilience and scale and multiple autonomous teams delivering software independently of each other, etc., etc. So don't fight reality. Instead, try to embrace reality, because it's a fact of life that information can only travel at the speed of light. This puts really a hard cap at the speed of information, the speed of how fast information can flow between things. This is really the reality of systems today, and this is not some esoteric thing that's only physicists deal with. It's actually something that we as computer scientists actually experience very often today. That this delay matters nowadays. Things move so fast. So this means in practice that everything we see, everything, even we as humans, everything we hear, see, feel, touch is actually, remnants from the past. If we observe something, it has already happened, often quite some time ago, actually. And so we're sort of always just looking into the past. It's always in the eye of the beholder. And the present, the thing that we take, for granted as being now, is actually relative. We all experience the different now. And this has sort of huge implications on how we build distributed systems, where latencies actually has a big effect. Okay, I'm not going to use this one anymore. So as soon as we exit the boundary of the service, we enter sort of this wild ocean of non-determinism. That's what we call distributed systems. That's the space between these services is the space where everything can fall apart, where the systems can start failing in the most spectacular ways. Where messages get dropped, reordered, garbled, etc. So this might sound terrifying, and to some extent it is, right? But it's also this space in between. This creates a non-deterministic space in between services, the network, that sort of gives us solution for things like scale, for things like resilience, for things like full elasticity, for things like isolation, etc. But in order to stay sane in this world, we need to be able to model uncertainty, because it's really all about uncertainty as soon as you leave this safe zone of the service. And I think it's extremely important that we don't sort of try to hide the network, hide the complexities, like it's been done in the past multiple times, like RPC, XA transactions, I mean, Corba, etc. I mean, it's distributed objects in general, I believe, is a sort of flawed approach to this problem, because we try to hide away too much. It's sort of a convenience that that sort of leaks. You know, Joel Spolsky talks about the law of leaky abstractions. This abstraction leaks too much to really be useful in this sort of extremely hard world, or complex world. It's better to just go tackle these things head on. And you know, Pat Helen said that in a system which cannot count on distributed transactions, the management of uncertainty must be implemented in the business logic. It's our job to actually implement that. And I believe it's actually not that hard, because once again, if we step back and map reality to our software, a lot of things actually fall into place. And I really believe that events can lead to greater certainty. So if we model the world as events and how events flow, you know, workflow, then it can really help us get quite far on this journey. You know, Mark Burgess, he did a talk on Monday, I think it was, about promise theory and other things. I mean, he said that an autonomous component can only promise its own behavior. Okay, autonomy makes information local, leading to greater certainty and stability. You know, I can probably give a whole talk on promise theory, which I think is a very interesting way of viewing the world that's highly relevant to the world we live in today. But I'll just sort of give you this quote and let it try to sink in a little bit, because I think this sort of, the fact that autonomy makes information local and that a service only can promise its own behavior, not others, you know. It can have profound impact on how we design protocols that actually are can sort of help us sort of thrive in this very hard world. And I think events can also then, the inverse of this non-deterministic ocean, you know, is that events can also help us sort of craft this autonomous island of determinism, that, you know, within this island, you can sort of assume strong consistency if you do it right, and we can actually live happily under the illusion that time is absolute, at least on our little island, that there is a single present, that there is a single now on our little island, you know, and we just focus on that and not worry about, you know, the crazy world outside our little component. And then we define, you know, well-specified protocols that receive and emit events that help us to connect these little islands of sanity, or whatever we want to call them. It's also important, you know, because as Sidney Dekker says that accidents, they come from relationships, not broken parts. It's from his great book, Drift into Failure. It's really not, it's a book about general, you know, sort of systems thinking in terms of failure. It's not really related to computer science. Because it's only when you start sort of like putting things together into more or less complex, more and more complex scenarios, like complex systems, that accidents sort of really fully materialize, let's say. And as Richard Cook said in his really, to me, influential paper, how complex systems fail, is that complex systems run as broken systems. And in a complex system, something is always failing somewhere, okay? That's a fact of life. You better, I mean, so having some sort of strategy where we try to prevent failure is not sustainable. Right? We need an approach where we fully embrace failure and bring it in, you know, and have it part of a programming model. That sort of failure is a natural state in our component life cycle. because it will happen. We will end up in that state. Instead of sort of trying to be scared about it and try to prevent it at all costs, we should embrace it and make it and look at it as something natural, something inevitable. So a lesson that I personally learned the hard way is that resilience is by design. Okay? There's really nothing that you can sort of bolt on afterwards. Way too often I see people building systems, beautiful systems, thinking about everything will go right, and then they sort of at the end of the application development life cycle, they think, oh, we better deal with we handle resilience, sort of high availability, and they sort of just think they can sort of like slap that onto the service or onto the system, either by like turning on WebLogic clustering or WebSphere clustering and hope for the best, etc. Or like sort of slap a data grid on top of it, like put the shopping cart there and hope everything will be fine. But it's the thing is that that's not a sustainable strategy, because since failure can happen anywhere and it will happen, it's better to just build it into the life cycle of the app, of the components themselves, to sort of design around resilience. This is a photo of a home in Texas that was sort of designed to resist floodwaters. And it was one of the few homes that sort of survived Hurricane Ike in 2008. So it's really sort of a good symbol for resilience by design. So I really think that we need to fundamentally change the way we think about failure in general. As I said before, failure is inevitable, failure is natural, failure will happen. It's really nothing exceptional about failure. It's sort of ironic that in Java or in a lot of other languages we call, sort of failures exceptions. Really, there's nothing exceptional about them. They are expected to happen, okay? So design for failure and try to manage it instead of preventing it. That's my philosophy. So what are the requirements then for a sane failure model? I believe that failure needs to first be contained, fully contained. And this helps if you build fully autonomous services. This really helps. You need full isolation, so you don't sort of end up with this sort of cascading failures. So like one failure, sort of taking down the next service because all your components are so strongly coupled. It takes down the next, it takes down the next, it takes down the next, and after, if not too long, your whole cluster is down. I've seen this way too many times. So contain the failure to avoid cascading failures. You need to reify the failure as events. If you have a fully event-driven model, then events sort of model the life cycle, the communication flow of your system. If you make failure sort of something natural, that's also information that needs to flow. That's also communication, okay? So then it's natural to look at failures as just events that flow alongside the rest of your events, okay? So reify them as events. You need to signal them in a fully asynchronous fashion. If you don't signal them in an asynchronous fashion, then you end up with a strong coupling, and that sort of can start taking down systems. And then they also need to be sort of observed, by one, or by 5, or by 10, or whoever many sort of listeners that you're into. You might want to have sort of one that logs it, one sort of that notifies whatever ops, one that sort of try to manage the life cycle of the component, restart it, etc. And it's extremely important again that you have this full isolation so you can manage the fail component in a healthy context. That if this component fails, that there's another component here that sits in a fully healthy state, and therefore can deal with the notification of failure and act upon it. Manage it by restarting it, by starting up a new component on another node, for example, if the whole node is down, etc. And all this is sort of enabled by thinking as failures as being events that just flow naturally as all the other information. But, you know, but all this stuff, you know, async, distributed systems, eventual consistency, uncertainty, talk about failure models, etc. It all sounds really, really hard, doesn't it? Yeah, I mean, if you're new to these things, it definitely does, right? It can be a completely different world if you're used to, like, you know, strong consistency, you know, synchronous method dispatch. There's always a way up, you know. If you send events, there's really no way back, you know, in terms of call stack. So the asynchronous nature of events can be quite a hump to get over. But I believe that, you know, so some people might feel like Calvin here. I've done it myself many times. But I think it can really help to just relax first, you know, and then take a step back, and then try to think in terms of workflow. Then if you do that, you know, then a lot of things will fall into place. Workflow is often very, very intuitive to most people. So think about your system, try to design your system through workflow. It helps. Then another technique that I will sort of dive into a little bit more detail is that really helps, I believe, building these type of systems and bringing all these things I've talked about together is what is now popularly called events-first domain-driven design. It's really thinking in events from head start in your design process. Okay, you know, domain-driven design. I mean, I'm sure most people here are familiar with it. I mean, founded by, you know, coined by Eric Evans in 2003, I think, and it's a great sort of methodology to designing systems. Absolutely, I've used it myself for more than a decade, and it's done a lot of good. But if you use domain-driven design, you know, sort of as written by Eric Evans in his first book, just blindly, then it can lead you to some problems, because I believe that you know, the original way of looking at domain-driven design is that it makes you focus on the domain objects themselves too early in the design. It means that you focus on structure too early. What are the things in the system is the primary thing that you try to model, okay? Greg Young said one in a talk that I attended some time ago, that when you start modeling events, it forces you to think about the behavior of the system, okay, as opposed to thinking about the structure of the system. I think this sort of hits right at the heart of the problem of focusing on domain objects too early. You lose a lot of things by doing that. So I think instead of focusing on the things, try to find all the nones, you know, that we have been taught to do in traditional object-oriented design for 20 years. We should focus on what happens in the system. Try to sort of find the verbs in the system instead of the nouns, because these verbs are our events then. So focus on events instead of domain objects. So I mean, when we come into a new design session, we should try to think like a detective. So try to like mine the facts. Ask ourselves, what are the facts here? Like elementary, my dear Watson. And one thing that can really help, a very useful tool that is quite new, but it's proven itself to be immensely useful, is something called event storming. It's sort of essentially that you bring all the stakeholders into the system, into one room, all the programmers in the same room, all the domain experts in the same room, and just let them brainstorm. Try to sort of mine the facts. Try to find the domain language and how to talk about things through the events. Focusing primarily, I mean, what happens in the system, okay? Understand how data flows in the system, etc. And try to understand things like causality. I mean, X happens that leads to Y, that leads to Z, whatever that might be, you know? Because that's really the essence of business logic. A lot more than the nuns, you know. They are passive. They don't do anything unless you put business logic. It's much more important to wrap your head around what's actually happening in the system, how data flows in the system, especially nowadays with all these data-centric applications. Then it's all about the data. And it's all about active data, data in motion. So what we need to do is we need to first try to understand, you know, the intents, sort of the intents, or first. But one of the things that we need to understand is the intents. Intents is like things like, what we need to look for when we try to find intents is like things like communication, conversations, expectations we have, contracts between different parties, transfer of control from one side to another side of the system, and then also try to find the facts. Then we look for things like state, history, causality, and one thing leading to the next, notifications of all sorts, you know, and transfer of state instead of transfer of control. And usually, I mean, the intents are then, can usually be mapped as what we call commands. Commands are always side effecting, okay? They represent, you know, the intent to do something, while, you know, the facts are sort of immutable facts of information. That's the sort of pieces of truth that you sent around, something that has already happened. Okay? So if we try to understand commands and events a little bit better, so commands is sort of the object form of a method, of some sort of action request. Okay? And usually you usually name them in the imperative, like create order or ship product and these type of things. Okay? The commands then cause reactions. Reactions are sort of like some side effects. I mean, if you don't have any side effects in your system, then the system is usually useless. It doesn't do anything. So you need to do something, react upon the commands that you receive. And out of those reactions, then, you create immutable facts representing what just happened as events and sort of share them. And so events are always in past tense, like order created, order has been created, the fact that order has been created, or the fact that a product has been shipped, product shipped, etc. Okay? So, but let's dig a little bit deeper then. So commands are all about intent. I want to do something. I'm asking you to do something here. While the events are completely intentless, they don't care. You know, they have really no intent at all. Commands are directed. I want someone to do something, then I send a command. A specific point-to-point communication. While events are fully anonymous. I shouldn't even have to really know who emitted the event. Often I do, of course. There might be reasons why I want to know who emitted the event, but really should be seen purely as a piece of information, and therefore anonymous. You know, commands have a single addressable destination. Events just happens for anyone that's interested to observe. It can be 0 if there are no interested listeners at this point. It can be 200. It can be anything. Okay. So commands, these are the model personal communication. I talk to you directly. While events, they model more like broadcast, or like speaker's corner or something. Like you know, this situation, I'm talking to you, I'm just trying to relay the truth here, you know, and you choose to accept it or not. And this means that commands, you know, they have a distributed focus. Because the whole intent, you know, is to ask someone in some other context to do something. It might, you know, sit right right next to you in the same process on the same JVM, but it can also sit in another data center. No, so it's really all about distributed communication. While events, they only happen locally. They emit locally what's happening. Then you might use sort of messaging, you know, to relay that event as a bridge, you know, to other systems. But from a theoretical standpoint, events are just emitted locally where they happen to anyone that's interested to listen in. So commands are really about command and control, which is useful, but in my opinion, you should use sparingly. You shouldn't use it more than you absolutely need to. Commands they have a purpose, usually to initiate some sort of effect on the system as a whole, but most of the logic are better driven with events, you know, because that gives us autonomy. So I usually try to favor events over commands. But as I said, commands are sometimes absolutely needed. And if you're familiar with domain-driven design, then I'll let the events define the protocols, that sort of defines the scope of my services, meaning the bounded context in DDD terms. And yet again, I mean, this sort of gives us a way to sort of try to model uncertainty, because then I can clearly distinguish between what do I control and what is outside my control. This crazy ocean of non-determinism versus this safe island that we can relax and, enjoy in. Patel, and also, he defines sort of a nice framework for how to think about this and think about consistency between services. He talks about inside data as our current present. That's the state we have within our service. Outside data, he talks about being the blast from the past. That's our events, the facts that flow between services, always representing something that has already happened some time ago, that we can choose to react upon. And between services, he almost poetically calls hope for the future. That's what he means by that is the commands that flow. I'm sending an intent for someone else to do something, and I hope that they will comply. Okay, it's from his paper, Data on the Inside versus Data on the Outside. See at the bottom there, if you want to read it. It's highly recommended. But events can also, as I said, alluded to in the beginning, be used as sort of this source of truth, to implement our service or record. We already have sort of these pieces of truth, of facts, flowing around in the system. So why not take advantage of them then? To model this in DDD, then we use the aggregate. It's no news here if you know domain-driven design. It is the aggregate that sort of maintains the integrity and the consistency of our service. Okay? It is our unit of consistency. It's our unit of failure as well, as we talked about earlier. It's our unit of determinism. You can assume strong consistency within the aggregate, which simplifies a lot of things when it comes to reasoning about data. Okay? This means that the aggregate is always atomic, atomic in acid. And it's fully autonomous as well. Okay? But I think it's important to understand that you shouldn't just blindly map this now to a SQL database. You're using ORM. I mean, you don't need update and delete any longer. I've already talked about you should not delete facts, and you should not update, mutate facts. Facts are immutable pieces of information. They only accrue. So that means that update and delete are gone, You just need create new events in an append-only fashion, following causality. One thing leads to the next, to the next, to the next. Knowledge just accrue, or read at any point in time, okay? So you only create and read, and not update and delete. Updating, because the problem with CRUD is really the updating place. Is that you can go in and mutate data. You can mutate facts, which is just wrong. Plain wrong, in my opinion. It just leads to a lot of problems. As Jim Gray once said, that updating place strikes the systems designer as the cardinal sin. It violates traditional accounting principles that have been observed for hundreds of years. Yet again, I think we need to let's just look at how does things work in the real world and try to map that knowledge to how we should build systems. Just relearn the basic principles of accounting and apply them in systems today. And I think we have a lot of unlearning to do here, which might be hard, And you know what happens when you like pull away a kid's favorite toy right from his hands, But It can be healthy as well. So we need to rely on the basic principles of regular bookkeeping, traditional bookkeeping. And the way we do that in systems is through a concept called event logging. I'm sure you've heard about it. You know, it's really nothing new either. I mean, that's how the Oracle databases or old SQL databases have worked for years. They have the transaction log that sort of stores all operations. But that is not exposed. They only expose this mutable view, being the table. That is essentially just a snapshot in time of how it happens to look right now, ignoring the historical data that sits underneath. Okay, but I think the event logging can really be sort of the bedrock, the stable foundation that we can build a lot of things on, like consistency, availability, scalability, traceability, auditing, etc. And Pat Helen again once said that the truth is the log. The database is a cache of a subset of the log. So it's really sad to just work with the subset, with the cache of the subset, when you can actually work with the real thing, when it's there, when it's fully available at all times. You know, there used to be a reason, I must say, that we used update in place. You know, disk space used to be very, very expensive. So there was a sort of a practical reason why update in place was a default like 20, 30, 40 years ago. You know, but today disk space is incredibly cheap. There's really no reason to keep on doing this anymore. Relation database has a lot of other sort of advantages, of course. For understanding data, making sense of data, relationships, and all these things. I'm not saying that we shouldn't use them, but they can just be a listener on the other side of the stream, keep maintaining its or copy of what the world looks like right now for you to run your reports, etc., right? But in my opinion, we shouldn't look at it as a source of truth. That should be our events. And event sourcing, I don't know if you've heard about that, but that is sort of a great pattern on top of the event log that helps us achieve this. It can be sort of a cure for this cardinal sin, updating place. And in event sourcing, since you have all the events that are already flowing in the system, in event sourcing, you simply store them in the order as they arrive, one by one by one by one by one. So you have the full history of what's ever happened in the whole system. Normally, you have perhaps one event log per aggregate. So that means that all the states the aggregate ever been in are recorded, on disk in the order they happened. And there's a lot of advantages to this. I mean, this means that we can do things like, for example, on failure, we can simply just replay the event log, bringing the component up to the state it was right before it failed, and continue serve. We have things like replication already solved because we can have any number of listeners to this event log, maintaining each one their own copy of the data that is now as hot as the master. We have like rock solid auditing. The auditing is the event log. We don't need to have yet another system to do auditing and sort of debuggability and things like that. We can just inspect the log directly. So a lot of things are unified using an event log. So and the way it works is like, let's say, first talk about the happy path here. We sort of receive and verify the command that we get to the component. For example, approve payment in this case. We create a new event then after the fact that we have approved the payment. For example, payment approved. We append it to the event log. And if it has been successfully stored on a durable medium, then we update the internal component state. And then we sort of run the side effects. when we know for sure that we have stored the event in a durable fashion. Okay. However, in the SAD path, then the only thing we need to do then is to rehydrate the events from the event log, and then update the internal state. We do not run the side effects, for example, because they have already been executed once. We're only interested in bringing up the component to its current state. And here the component has sort of the snapshot of what sort of the state looks at this point in time, while you retain all the history that's ever happened in the event log itself. And this is what Martin Fowler sometimes calls memory image. If you Google memory image service, this is usually what he means, that you have sort of a durable representation of your object state. So it's sort of persisted in memory, you can say. And one of the benefits with this is that it sort of gives you one single truth of all history that's ever happened, as I already said. It allows for this durable in-memory state, and it sort of helps us avoiding this, this traditional object relational impedance mismatch. There's really no need to sort of map your object state now into relational tables. As I said, you can do that, but that's not the job of the component or the persistence system. That's something you can sort of have a subsystem or another system subscribe to, You can have different sort of views on the state. That's what I'm talking about. Some people talk about CQRS as sort of a pattern to achieve that. Where if you have multiple views, when each representing the state in the most optimal way for how you want to use that. If you want to run reports, then you can have a SQL database subscribe to the event log changes, maintaining a perfect view for reporting and data mining. If you want to reduce big data analytics on it, then you can have, for example, push it down into HDFS and have Spark or Flink or someone else pick that up and sort of maintain their view on the data, etc. While for within the service, you simply maintain your in-memory representation. And finally, I mean, this way of working with sort of an append-only log usually has really good mechanical sympathy. Mechanical sympathy is sort of a term that Martin Thompson usually talks about. It's sort of the idea of building software that are in line with how the hardware works. They're in line with like how modern processors, memory systems actually work. And having things like, for example, append-only log means that we can have a single writer that can sort of write down in an append-only fashion to disk fully uncontended in extremely fast fashion. It works really well with SSDs, for example, and things like that. Some disadvantages, though, of using something like event sourcing and event logging is that it's sort of an unfamiliar model to a lot of people. It's a leap of faith. It's also something that perhaps doesn't fit all systems. But if you sort of approach system design from the world of events, it fits like a glove. Since you already have the events flowing, why not just take advantage of that and just store them in the order that they already flow, and you're basically done already. So I think there's a lot to gain from trying to view the world from events from a persistence perspective as well. Other disadvantages is they can be hard to version events, for example. That's something you need to take into account. If you want to sort of change, sort of upgrade this is sort of the way you view state. You need a way to have sort of some sort of translation layer between old events and new events. That's often happened perhaps in the anti-corruption layer that you put in front of your service that does this sort of translation, etc. But there are some things to think about. Or deletion of events, like this new law sort of stated by the EU, that you actually are in some situations forced to delete events. How do you do that? There are different ways of implementing that. You can sort of, for example, encrypt all the events, and then in the case of In the case that you have to delete them, you can just throw away the key, or you can actually go back and physically delete them, even though conceptually that's the wrong way of doing it. You know, this is the wrong way of viewing the world. But sometimes it's needed for pragmatic reasons. So I'm almost running out of time. I just quickly want to talk a little bit about how events allow us to manage time as well. So, you know, modeling events forces you to have sort of a temporal focus of what's going on in the system. That's also important. The time becomes a crucial factor in the system. And so event sourcing also allows us to have a stable notion of time, have to model time. You know, because events is sort of the snapshot in time, or ID is sort of an index for time. It's sort of logical time. You know, and I said, once again, the event log is a full history, so it's the database of the past, not just the database of the present. But it's the database of the past and our path to our current present. And the interesting thing is that it allows for things like time travel. You can go back in time and sort of replay the log for things like historic debugging, understanding why something went wrong. You can just run a replica in a safe zone outside and just replay it like one by one by one, I mean, as slow as you want, and try to understand what actually happened. For auditing and traceability, I said, replay the log on failure, replay the log for replication, and even do funky things like forking the past, if there are reasons to do that, or even sort of join two distinct pasts. There's a lot of, it gives you a lot of sort of power in how to work with time, and for everyone that's worked with distributed systems, like working with time is probably the hardest thing you can do in distributed systems. So have a stable notion of time and working with logical time in a natural fashion, you have a lot to gain, in my opinion. So key takeaways, if I sum up, events first design helps you to move faster with less risk, building scalable and resilient systems. It helps us, you know, to achieve this thing everyone talks about with microservices, fully autonomous services that can be developed by autonomous teams, you know, well-established protocols in between that take versioning and all these things into account. And helps us balance, you know, the certainty and uncertainty, and having, you know, boundaries for that. So we know when we're stepping from one zone to the next, and why we do that. Okay. And event logging can really help us things like avoiding CRUD and avoiding ORM at all, unless you absolutely need to maintain a secondary view. Take control over the system's history. Things like time travel, so like for auditing and all kinds of things, and help us balance, you know, in strong consistency and eventual consistency. Strong consistency within the aggregate, while eventual consistency in between, just to give us more headroom for scale and resilience. So, I mean, I'm biased, but Akka can really help you with that. It was sort of built with for these type of systems in mind. It has, you know, event sourcing built in. It's fully decentralized. You have these unit of services that are fully autonomous. Failure management is all built in, etc. And if you want to learn more, I wrote a little book for O'Reilly on this. It's freely available from this URL. It covers some of these things in more detail. So sorry I ran over time a couple of minutes, but thanks for your attention.